everyone. This is kind of a special edition of our regular kind of weekly program. What I want to do today is just go over the 6 answers to the review problems. So this is a little bit different. What I want to try and do is give you some background information that's going to help you prepare for the exam, kind of go over what some of my thoughts might be as I'm developing the exam. So I'm going to mention a bunch of those things as we go through the problems. If you were unable to join one of the Zoom sessions today, then this video is for you, or if you joined late, this video is for you, because I'm going to go over what we discuss in some of those sessions and any other ideas that I have as far as what problems might be for your exam coming up on Tuesday. So, a couple of things. Number one, the exam is going to be 6 questions. That part's not going to change. The order of the questions is going to be exactly like the order that we're going to do as we go over it. So the first question, even though it might be different for different people, is either going to be a Boyle's Law, a Charles Law, or a Gay-Lussac's Law problem. That's going to be the same for everyone. So I'm going to get started with problem number 1. I'll read the problem to you. I'll go over how to do the answer. I'll talk about some hiccups, and then we'll move on from there. So problem number 1, it says, a rigid metal tank for compressed gas at the local Sunoco plant has a maximum safe pressure limit of 825 kPa. Now, when I post the answer key to this later today, one of the things that you're going to notice is that I tried to be very descriptive in terms of places where students might get tripped up. And we're going to start off right with that. It turns out when you read the full problem, that 825 kPa is actually not P1. It's going to end up being P2. So the design of the problem here is to try and catch anyone who is not reading the problem and is just skimming for numbers, and they say 825 kPa, bam, that's a pressure. I'm going to write that down as pressure number 1 because it's the first one I came across when I did the problem. You have to read these problems. You have to read the problems on Tuesday when you take your exam and look out for pitfalls like this. So if you continue reading the problem, it says, the pressure gauge reads 388 kPa when the pressure is, when the temperature is 24.0 degrees Celsius. It is actually those that are pressure 1 and temperature 1. So 388 kPa. And in this case, temperature 1 is 24.0 degrees Celsius. One of the, so we already saw pressure 2, by the way, 825 kPa, and temperature 2 is what we're looking for. One of the questions that I get asked most often is, does my pressure have to be in a specific unit? And it's kind of a difficult question to answer because in some cases, in some problems, yes, it does have to be in a specific unit, but in other problems it doesn't. So how do you know? Well, if you're using R, the letter R, the universal gas constant, or the variable that you better know as PV equals nRT, if you're using that type of R in a problem, then yes, you have to be in units of ATM. But in any other problem, the unit of pressure is not really relevant. It doesn't matter what unit you're in. So you could be in KPA, you could be in MMHG, and you're still going to be able to solve the problem. Now keep in mind, sometimes a problem is going to present you with 2 different units. So you're going to have to pick one and convert to that. They do have to be in the same unit, but it doesn't matter for the most part in this first problem what unit you are actually in. All right. So the question says, what is the highest Celsius temperature? So again, just be on the lookout for something like that. You might think you're done with the problem when you calculate the final temperature, or we're going to have to go back and do one additional step. So we're going to use, in this problem, we're going to use Gay-Lussac's law. So we're going to start off with pressure 1 over temperature 1 equals pressure 2 over temperature 2. And of course, we're solving for temperature 2. Now, as the homework problems have been coming in, one of the things that I've noticed is that many of you are saying, temperature 2, I'm going to solve for that. So I'm going to move pressure 2 down here and I'm done. Nah, you can't solve for a variable when it's on the bottom. You have to move it to the top. So the very first thing I'm going to do is I'm going to move temperature 2 up here. I'm going to get rid of it down here. So let's get rid of all this that I just added. So I'm going to get rid of it from down here. Now that temperature 2 is on top, I can move things away from it. So now I'm going to move T1 up here and P1 down here. So I'm going to wind up with temperature 2 is equal to P2. T1 is going to move up here, so I have T1 over P1. Now I can plug in my variables. So I have pressure 2, 825 kPa, times temperature 1, 24.0 degrees Celsius. Of course, we cannot use Celsius temperatures. We have to convert all of them to Kelvin. That's something that's universal, so regardless of what problem we're doing, that has to be. So in this case, I'm going to add 273.15. So I'm going to get 297.2 Kelvin. Now I can keep one decimal place because I had one decimal place here. So 297.2 Kelvin and divided by pressure 1, which is 388 kPa. So I made a note of this to some of the classes that I've spoken with today so far, and that is that I'm not going to worry too much about significant figures on the test. In fact, I'm not going to take off points regardless of whether you have too many or too few. However, units do remain very important. And the reason why units are so important is because they help tell you whether or not you've set up your problem correctly. So in this case, the fact that kPa crosses out is a good indicator that I rearranged my problem correctly. If you rearrange the problem incorrectly, there's a good chance that your units are not going to work out based on the way that you rearranged it. So that is also a good indicator and something that is very important to me. All right, so if I solve this problem, I wind up with a temperature of 632 Kelvin. They ask us to convert it back to Celsius. They want a final answer in Celsius. So this ends up being 359 degrees Celsius. This is normally where I would ask if anyone has any questions, but since there's no one here, I can't really answer any. All right, moving on to problem number 2. I'm just going to erase this. So I'm going to pause this for a second. Okay, and by the magic of TV, I am back, and we are ready to look at problem number 2. So in all cases, problem number 2 on everyone's exam is going to be a combined gas law problem. So I'm going to go ahead and write out all of my variables to start off with. So I have P1, V1, T1, P2, V2, T2. All right, reading through the problem. A sample of gas has a volume of 21.0 liters, 21.0 liters at a pressure of 78.0 atm. Oops, actually the 0.0 isn't there. And a temperature of 900.0 Kelvin. And the question says, what will be the volume? So we're looking for volume 2. What will be the volume of the gas if I decrease the pressure to 45 atm and I decrease the temperature to 750.0 Kelvin? Now, one of the things that I've been doing today is I've been going over the problems with students is just mentioning, hey, here are some other things that I could throw in there just to kind of make the problem a little more challenging. Perhaps when I give you pressures, I give you one in ATM, I give you one in mmHg. Again, that's a scenario where you'll have to pick one or the other and make sure that you are using 2 pressures that are in the same unit. Same thing with temperature. Could give you a temperature in Celsius and one in Kelvin, and you would of course have to change that Celsius temperature to Kelvin. So my combined gas law equation, P1 V1 over T1 equals P2 V2 over T2. In this case, I'm solving for V2. Again, a different twist on this problem could have you solve for a different variable. I especially like having students solve for a variable at the bottom, because just like in the first problem, it makes sure that makes me aware whether or not you know that you have to move that variable up to the top if it's on the bottom in order to solve for it. Now we don't have to do that here because the variable that we're solving for is already on top. So I'm just going to bring P2 down. I'm going to shift T2 up. So I'm going to get V2 is equal to P1 V1 times T2 over T1 times P2. At this point, we have the variable that we're looking for. We can substitute all of our values in. So I'm going to have 78 ATM times 21.0 liters times temperature 2, which is 750.0 Kelvin. All of that divided by temperature 1, 900.0 Kelvin, times my pressure 2, which is 45 ATM. Again, the reason why I emphasize units, so here we're going to get ATM to drop out, Kelvin to drop out, so we're left with a unit of liters, which is good because we're looking for a volume, which should have units of liters. Plugging all of this into the calculator. When you're plugging it into the calculator, please remember, you have two choices here. You can put the bottom in parentheses, or if you would prefer, and this is what I do, I type in 78 times 21 times 750, then I hit divided by 900, and then divided by again, and then type in 45. So as long as you remember to divide by both of these things that are on the bottom, you don't even need to use parentheses. But if you're going to forget, then please use parentheses. So in this case, we get volume 2 is equal to 30.0 liters. So combined gas law, all three variables, pressure, volume, and temperature are changing, and we get a scenario like this. All right, I'm going to pause again. We're going to go on to question number 3 in 1 minute. Okay, we're back for problem number 3. Problem number 3 says we have 3 gases. Those gases are called gas A, B, and C, and they are confined to a 32-liter container. So here's my container. Volume equals 32.0 liters, and that inside of the container, I have 3 gases, A, B, and C. It says that the temperature is at the container rather, is at a temperature of 25 degrees Celsius. So I have 25 degrees Celsius here. You'll use that temperature so often that you will be able to convert it to Kelvin in your head, 298. The container has 1 mole of gas A and 2 moles of gas B. So 1.00 moles here, 2.00 moles here, and this is kind of our unknown. We don't know how many moles of gas C there are. If the total pressure inside of the tank is 3 atm, calculate the moles of gas C. So pressure inside of the tank is 3 atm, and again, we're looking for moles of gas C. Now, the way I'm going to show you how to do this problem, I'm actually going to show you 2 ways. The way that I'm going to show you how to do it first is the easier way. I actually thought of this after I did the problem. And then I'll show you how it could have been done a different way. So we're going to use PV equals nRT. So because we're using R, we have to make sure that our variable for pressure is in ATM, our temperature has to be in Kelvin all the time, and our volume has to be in liters because R, that universal gas constant, has all 3 of those liters embedded in it. So in order for our calculations to work out, we need to make sure we're canceling out those units. So in this case, since I'm looking for a number of moles, I'm going to solve this equation for N. So I'm going to get N is equal to RT, come under here. So I'm going to get PV over RT. In this case, my pressure, 3.00 atm. My volume, 32.0 liters. R, 0.0821 liter atm over mole Kelvin. And my temperature in this case, 298 K. Now, when I solve for moles here, this is actually the total number of moles that are in the container. So when I solve for moles in this case, I get the total number of moles to be 3.92 moles. So now to find the moles of C, I would just subtract out the moles of A and B. So moles of A 1.00 moles. Obviously, you could do this in your head. Moles of B, 2.00 moles. And I wind up with 0.92 moles, which is my moles of C. So that's the easier way that I figured out how to do the problem. When I designed it, I was trying to make it a Dalton's law problem. So the original idea was, all right, I give you some variables here, and I give you A and B. So you would find the partial pressure of A, so that would be moles of A times R times T divided by V, and that would give you partial pressure of A. Then you would do the same thing for the partial pressure of B, moles of B, R, T divided by V. Then, using Dalton's law, you would add these up. So pressure total is equal to pressure of A plus pressure of B plus pressure of C. So if you knew the total pressure, 3, and you knew the partial pressures of A and B, you could get the partial pressure of C. So PC, partial pressure of C times volume times N of C times R times T, and then you would solve for moles of C this way. So partial pressure V over RT. This is actually how I wanted you to do it, so that you would have one pressure calculation, a second pressure calculation, use Dalton's law, and then solve. But then I thought of it an easier way to do it. So I wanted to show you both ways. That way, in case you use one or the other, you would see both ways. On the answer key, just so you're aware, I showed you both ways. I actually showed you this way first, and then below it on the answer key, I showed you this way. So when you're looking at the answer key, you'll actually see both of them. All right, well, there are no questions because none of you are here. So I'm gonna pause for another minute. I'm gonna erase this one more time, and then we'll go over problem number 4. Okay, so problem number 4 for everyone's exam is going to be a Graham's law problem. If we take a look at problem number 4, it says 2 gases, unknown gas A and nitrogen gas. So, unknown gas A, and then nitrogen gas. I still managed to trick a few of you. Remember, nitrogen is a diatomic, so its molar mass is 28.02 grams per mole. In case you're wondering, just to review the diatomics on the side here, the diatomics, remember, are H2, N2, O2, F2, Cl2, Br2, and I2. However, not all of the diatomics are gases. So bromine is a liquid and iodine is a solid. And again, that has to do with the strength of their LDF. So the ones that are smaller molecules, they have weaker forces of attraction. Thus, these end up being gases. This is something that we talked about earlier in the year. And then, of course, bromine with its larger molar mass, and then iodine, those tend to be liquids and solids. Sorry about that. Okay, by the way, that question or that aspect came up a few times on the gas laws and stoichiometry homework. So you had to remember in that very last problem that Br2 and Cl2 were both diatomic. And you had to remember that because Br2 was a liquid, it did not get included in the number of moles that went into calculating that final pressure. So when we use gas laws, the number of moles that we're talking about can only correspond to moles of gas. It can include the, in that case, NaBr, which was a solid because it's an ionic compound, or the NaCl, which is a solid because it's an ionic compound. All right, getting back to our problem here. It says these 2 gases are confined in a 6.00 liter container. Turns out that that piece of information is completely irrelevant. So yes, they're in a 6 liter container, but it really doesn't matter for this problem. The container develops a small leak. The unknown gas effuses faster. So shooting out of this faster is the unknown gas. at 3.72 times faster. That's important. Because the unknown gas is faster, the unknown gas is the lighter gas. So because unknown gas diffuses faster, it must be the lighter gas. Some of you are saying, so what? Who cares what gas is lighter? Well, it turns out that it's very important when you're setting up your problem that the heavier gas goes on top and the lighter gas goes on the bottom. So I'm going to show you that right now. So this part, doesn't matter what you write over here. Remember, this is just the ratio of rates is equal to molar mass 2 over molar mass 1. This has to be the heavier gas this has to be the lighter gas. So this 3.72, that part's going to go here. There are no units on that. Square root sign. The heavier gas, in our case, the heavier gas is nitrogen. So we have 28.02 grams per mole over X. In order to solve something that has a square root, typically what we do to get rid of the square root is we square both sides. So when we square both sides, in this case, we're going to get 13.8 over here, unitless, no units on that, is equal to 28.02 grams per mole over X. Now, we are still making algebra mistakes. Some of the homework assignments that have been turned in already solved for X by taking 28.02 and putting it under here. And you wound up with a molar mass of 0.5. You can't have a molar mass of 0.5. Hydrogen is the smallest atom, right? It has a molar mass of 1.01. So you can't have a molar mass of anything that's smaller than that, because then you're just talking about fractions of an atom. So in this case, we wind up solving for X by moving X up here, right? Because in order to solve for a variable, it has to be on top. And then we move the 13.8 down there. So we get X is equal to 28.02 grams per mole divided by 13.8 grams per mole. So X turns out to be 2.02 grams per mole. Of course, there's only one molecule that exists that could have a molar mass that small, so that is hydrogen. Remember, the next smallest element, which is helium, has a molar mass of 4 grams per mole. So if you get a molar mass of 2.02 grams per mole, you kind of know what your molecule is. Okay, questions on that? Again, if you have questions, please submit them through Schoology or email me. And not going anywhere, so I'll be here all weekend to answer any questions that you have. Okay, we're going to pause it again. And we're back for question number 5. So question number 5 is going to be our ideal gas law problem that uses density. So this problem is kind of unique. I'm going to show you 2 different ways to do it. It doesn't really matter. It's not exactly perfect, but it doesn't really matter which way you do, which way you use. I'm going to show you the easier way first, and then I'll explain why I'm going to show you a second way. So this year, basically, since we're in this type of situation, I'm not having you memorize any of the equations. You're going to be allowed, because there's no way to really stop you, you're going to be allowed to use any equations that you have at your disposal. So for this problem, I would expect that you're going to use this equation. Pressure times molar mass equals density times R times T. So reading question number 5. An unknown gas has a vapor density of 1.78 grams per liter. And it is at a pressure of 1.55 atm. And it is at a temperature which is 24 degrees Celsius. This time we have 2 decimal places, so we can actually keep our 2 decimal places here. So we get 297.15. we want to determine the molar mass of the gas. So we're looking for this. So we're going to get molar mass is equal to density times R times T divided by P. Plugging in 1.78 grams per liter times R 0.0821 times our temperature 297.15 Kelvin. All of that divided by pressure 1.55 atm. Looking at our units, we have liters, drops out, atm drops out, Kelvin drops out. So we have moles on the bottom, grams on top. That's perfect because we're looking for grams per mole. Excuse me, I've been speaking so much today. So we wind up with a molar mass of 28.02 grams per mole. Now, previously, in years when I taught this, we didn't have this equation unless you memorized it, in which case you were able to use it. But what if we didn't have that equation? So we can use our regular PV equals nRT to answer this problem. The only thing is, when we have density, 1.78 grams per liter, we're going to break that up into two pieces. We're going to have a mass that is equal to 1.78 grams, and we're going to have a volume that is equal to 1 liter. So if I were to do the problem this way, now I'm solving for moles. So that's PV divided by RT. So if I'm getting this by itself, RT come down here. Now I can plug in. So my pressure in this case, 1.55 atm. My volume in this case was 1.0 liters over 0.0821 times my temperature, which in this case is 297.15 Kelvin. When I solve that problem, I wind up getting a number of moles that is equal to 0.0635. So you're probably saying to yourself, hey, that doesn't answer the question, right? We're looking for molar mass. Molar mass has to be mass, grams, divided by moles. We have the bottom part. Where's the top? Well, the top is right here. When I separated out that density into 1.78 grams and 1 liter, I used the 1 liter here. Now I'm going to use the 1.78 grams. So 1.78 grams divided by 0.0635 moles turns out to be 28.02 grams per mole. So different way to do it. This is a way that you could do it where you wouldn't have had to memorize a second equation for the ideal gas law. All right, we're going to pause one last time while I erase this, get a drink of water, then I'll come back and look at problem number 6. Okay, we're back to take a look at problem number 6. I have my water. It's probably one of the few benefits of this environment. So problem number 6 is our gas law with stoichiometry problem. So if you have questions on this, again, please send me a Schoology message or an email. So the problem says 5 grams of liquid ethanol. So C2H5OH, this is a liquid. We have 5 grams of it. 5 grams of liquid ethanol is burned in a complete combustion reaction. So we have to go back to some prior knowledge. Means I'm combining with oxygen. I'm forming carbon dioxide and water. In this case, the problem tells us the products of the reaction are confined to a 30-liter container. So our volume is equal to 30.0 liters, and our final temperature is 600.0 degrees Celsius. That's 873.2 Kelvin. We can keep one decimal place in this case. Assuming no excess reactants are present, that means all of the oxygen that I have gets used up and all 5 grams of my ethanol get used up. What is the pressure inside of the container? So the pressure inside of the container at these conditions. So we're looking for pressure. That's our unknown. Well, if I have pressure, if I have volume and temperature and I'm looking for pressure, I always know R. I also need to know the number of moles of each of those gases. So I'm going to have to figure out how many moles of each of those gases I have in order to find out what the total pressure is going to be. So to do that, I need to balance this equation. So when I balance it, my coefficients are going to be 1, 3, 2, 3. So 1 ethanol combines with 3 oxygen, produces 2 carbon dioxides and 3 waters. So now my first step here is going to be to take all of my ethanol and figure out how much carbon dioxide I make. So to get out of grams, some of us are still forgetting this part. So to get out of grams, I need to look up the molar mass for ethanol. So that's 46.08 grams. And then of course I need to use my mole to mole conversion next. So 1 mole C2H5OH, 2 moles CO2. And for the first part, I end up getting 0.217 moles of CO2. Now, because I need both carbon dioxide and water, I'm going to do the exact same thing. By the way, I don't have to go to grams of water because we can't put grams into our PV equals nRT. We can only do that with moles. So I have 0.217 moles of carbon dioxide. I'm going to set this up again, 5.00 grams of C2H5OH. 1 mole, 46.08 grams. Times, this time it's going to be 3 moles of water over 1 mole C2H5OH. And that number turns out to be 0.326 moles. CO2. If I add up those 2 mole amounts, I'll get the total number of moles, which is 0.543 moles. So if I am looking for total pressure, I have PV equals nRT. P is going to equal nRT over V. Now, I need to solve this equation at 2 different temperatures. So I'm going to split this. For the first one, this is going to be at my 600 degrees Celsius, which is 873.2 Kelvin. I have pressure is equal to the total number of moles, 0.543 moles, times R, times temperature, divided by my volume, which is 30.0 liters. So pressure turns out to be, in this case, 1.29 atm. Now, and you'll probably have something very similar to this on the exam. In our follow-up question. It says the temperature is then reduced to 50 degrees Celsius. We have about 323.2 Kelvin. At that new temperature, at 50 degrees Celsius, water, sorry about that. I was supposed to say water. At that new temperature, water is no longer a gas. So water condenses, it is now liquid. It cannot go into the value for N. So instead, for this part, we're going to find pressure. The number of moles is only going to be the moles of CO2. So that'll be 0.217 moles times R times T divided by our 30.0 liters. And at this lower temperature, we get pressure equal to 0.192 ATM. And if you stop and think about it, that makes sense. We should get a lower pressure, sorry about that. We should get a lower pressure because of two things. Number one, we decrease the temperature. So decreasing the temperature, pressure and temperature are directly related. So if temperature drops, pressure should also drop. But, and perhaps more importantly, we have fewer moles. So we have less moles of gas, so of course the pressure is going to be reduced because we have less things that are in the gaseous state. Okay, that finishes up the review. Hopefully you watched one of the Zoom sessions. If you didn't, I hope you enjoyed this. If you have any questions between now and the day of the test on Tuesday, May 5th, please send me a message through email or Schoology. Thanks very much. I miss seeing all of you guys. Talk to you soon.